Hello, everyone. My name is Nicholas Wiley, and today we are going to be discussing the um, pressure forces that are given off from a liquid inside of a cylinder or a barrel on the barrel surface. So, over here we have a diagram. We'll just hop right into explaining everything that we know about this to begin with. So, the first thing that we're going to talk about is that this cylinder is a given length L that's going to be constant throughout all of this. In addition, we are going to have two different pressure forces. We're going to have a pressure force that is going to be on the um, cylindrical part of the cylinder, the cylindrical surface, curved surface, and then we are going to have a second force, which is going to be put off on the end caps by the fluid. Now, what do we know about this fluid? A couple things that we know. First, let's talk about the property of fluid. The pressure that they're going to be given off, the pressure that's going to be given off by the fluid is going to be rho, density of the fluid, which we know, multiplied by the gravitational constant, which we obviously know, and then h, the height. So what do we know about the height? Well, the first thing that we need to distinguish is what's going to be positive and negative height for us. As you can hopefully see from this, what we have is we have the top fluid of this, which doesn't have to be at the very top of the cylinder. It could even be somewhere along that line. So this right here is going to be 0 for us. And then the bottom of it is going to be h. Now, why are we distinguishing it like this? Well, as you go down in height, or I guess up in the height, we'll say down for now, as you go lower and lower, as you go to the bottom of the cylinder, the pressure that's going to be given off by that liquid at that point is going to be the highest. Now, why is this? Because as you go underwater, even in the ocean, there's going to be a lot more pressure as you go down. So we're going to denote that as positive just so that all of our expressions are hopefully going to remain positive. There's going to be a lot of integrations and things necessary that are going to give us negatives, but at least for our first force along the rounded shell of this cylinder, it's going to be positive. Okay, so how are we going to distinguish this? We have a rounded surface. Now, one thing that we can do, this is going to make this first force right here a lot easier to integrate and sort of understand, is we can make this into a plane. Now, why am I drawing a rectangle? Because I can't draw 3D planes. But what we can imagine is, as you can see here, imagine that you're looking down the spherical shell, not spherical, the cylindrical shell of this system. What we can do is we can put a plane going directly down at a length L, and we can just imagine that those forces are going to be perpendicular. Okay, so and that's going to help us in the long run, and it's also accurate in our integration and in our expression in the end. So what are going to be the dimensions of this rectangular plane that we're putting through? Well, we know it's going to have that given length L across. Now what we also know is that it's going to also have this h value, the certain height of the fluid. Okay, so what can we do with this now? We know that it has a certain length L and a certain length h, but how is this going to help us determine the actual force? Well, one thing we know about this is that no matter where you go along here, so we go here and here, those are both going to have the same amount of pressure, the same amount of force being exerted. But as we drop down by a certain small area we'll call dh, then it's going to change just from here to here. So what can we do? The whole point of integrating is that we're going to integrate along this area of this rectangle. So what is going to be our differential area that we can use? Well, simply, it's just going to be dA is going to be equal to L dH. As I've explained, all of these little chunks are going to have the same along the horizontal, and then as you change the height, it's going to change. So we're going to integrate from our, I guess, low point at the top to our high point at the bottom. I know that sounds very weird. I guess I could call it positive and negative, but either way, let's just get into it. So what do we know about our force in this situation? We know that our force, this F1, is going to be equal to P pressure multiplied by our differential area. What I'm going to do, I'm just going to erase this. So what can we do with this? We're just going to do some simple plugging in, and we'll get right through it. So for this P value, I'll substitute in rho GH, and for dA, substitute in down here. So what are we going to be left with? I guess I could erase some of this, give me some more room. I'm also going to be cutting in between parts just to ensure that we have enough room, make sure that it's organized and more easy to follow along with. but let's continue. So we have this pressure value. So we're going to have F1, the force exerted on the curved surface of our cylinder. It's going to be equal to P. We substitute in rho G. And what I'm going to do is I'm going to stick these constant terms out here to save time and make it a lot more clear as we go. So I'll cross that out. The rho and the G are gone. Now H is going to be changing down here, so it cannot go outside of the integral. And then down here for the dA, we have LdH. Now what I've told you before is that the L is going to be constant, the length is going to be constant. As you go along, we had that rectangular plane, and as we went along the length, nothing changed. It only changed at this differential height. So just to quickly run through why that's a constant, so we can throw that out here, the L. What we're going to be left with is the integral of h dH. Now I know that this looks very simple, but wait until we get to the force from the end cap. It's going to get very difficult, but we're just going to start it off easy, ease into things with our first force. So how are we going to integrate this? Well, first what we need to do is make these dummy variables of integration. What are we going to integrate from? Well, we're going to integrate from the top of the fluid down to the bottom. So the top of the fluid is going to be 0, our lower bound, all the way down to the bottom of H. So, no erasing necessary. So what's this going to be? All this is going to be is 1/2 h squared evaluated from 0 to h. Now we plug in 0, that gives us 0, but when we plug in h, it's simply just 1/2 h squared. So what we can do is we can get a final expression of our first force along the curved shell of our cylinder. It's going to be equal to 1/2 rho G L h squared. And that is going to be our final equation, a final expression for the first force that is going to be perpendicular along the curved surface of our cylindrical system. So what we're going to do after this is I'm going to do a little cleaning. I'm probably going to throw that down in the corner, and then we're going to get into the second force. Hello everyone, we are back, and I have decided to clean the board, as I've said, and move this first force that we have derived and created an expression for. I've moved it down to the corner to give us space for this next step. This is going to take a lot of room, so there may be 1 or 2 more cuts, most likely just 1. But let's get right into it. So now we're going to be discussing our end caps. So let's simply just draw a circle, not the worst circle. And what we're going to have for this is we are going to have a certain fluid level, which is we're going to call H right here. And we're also going to have the center of our circle, looks pretty central, with some radius r. Okay. Now, before I get into really describing the system, let's talk about what we really want to get from this. What we want to do is we want to do the same thing that we did before. Before we had a rectangle, which was only 2 dimensions. We had the length and we had the radius. The length and the height, sorry, not the radius. Getting too ahead of myself. Now for this, what we have is we have a circle, which this is going to take some polar coordinates, 3 dimensions. I guess not really 3 dimensions, but you know what I mean. Polar coordinates to really figure out this entire system right here. So let's just start with what we did before. Well, what do we know? We know that our pressure is going to be equal to rho GH. And what else do we know? We know that our force is going to be equal to the same thing. It's going to be the integration of our, I already forgot. Oh, our pressure and our differential area. We're going to integrate that, and we're going to be able to figure out our force. So what we need to do is we need to figure out all of these components right here. Rho and G are both constants, so we don't have to worry about that. So what we're going to need is H, and then the P we can just substitute in, and we need our dA. Now before what we had dA was going to be equal to LdH. Now the dH part, the differential height, is going to be the same thing, as I will talk about in a minute. Not the same thing, but it's going to stay in our expression for the differential area. But what we don't have anymore is the length, so we need to come up with a new variable, a new expression for the other aspect of our area. So let's just hop right into it. So what we have over here is we have our system. We have this circle right here. We have all of this fluid right here. And what we want to do is we want to integrate from one point to another point to determine the pressure. Now, what we're going to do is we'll just draw a line up here. We're going to draw a horizontal line right there, just to kind of set up our system. And then what we're going to be doing is we're going to be integrating from this point here all the way down here. So then afterwards, what we will do is we will multiply by 2 to get the rest of our area of our end cap. But either way, let's just keep rolling with it. Getting too ahead of myself. So the first thing that we can look at is what this H term is going to be. Now, what is that going to be? So what we have is we have this R value. So from the bottom up until the center, we are going to have that. It's going to be one aspect of our height. And then we have this H right here. We have this right here that we need to figure out. Well, as you can see, I've drawn a triangle because that's going to help us. Because what we're going to have is we're going to have this theta value. And what's this right here? That's also going to be our radius, as it's from the center of the circle out to the edge of the circle that we have. So that's inherently going to be the radius. So what do we do now? Well, we just start making an expression for height. So what is our height going to be equal to? So like I've said, we have this R value right here. That's going to be a big component of our height. It's going to be R, here to R. Then what is this little vertical part going to be? Well, that's the vertical of a triangle, of a right triangle. And as we know from simple trigonometries, we know that sine theta is going to be equal to opposite over hypotenuse. Sine theta is going to be equal to opposite over hypotenuse. And then with a little bit of rearranging, we would get that it is going to be R sine theta, and that's going to be our height. Right? Because we would have sine theta is equal to this right here over R, move the R, multiply it over as it's in the denominator, and you get R sine theta. Okay. Now what else can we do? We can derive this to get that DH term I told you that would be sticking around. But instead of just being DH, the differential height, we actually have an expression that we have to derive to get that differential height. So I'll just talk about it. I'm just going to write it out and explain it as I go. So we have our differential height. So this is just going to be, what we'll do is simply just derive this, get rid of that, so it's not confusing when we plug in later. So our differential height is going to be equal to the derivative of this. Now, what is the derivative of this? This R value is a constant. What's the derivative of 1? It's going to be 0, so forget about that. R sine theta. Well, we know that the derivative of sine is going to be cosine. So what we're going to be left with is R cosine theta. Okay, we're getting somewhere. So we have this H, we have this DH. I told you that L term is going to be replaced with a different constant. So what we're actually going to have is we're going to have these little chunks right here. Before this was the length, now we're going to call this the width. Okay. So what is this width value going to be? As well, I guess before I really talk about it, the width is going to be a constant as you go across. Constant pressure across here. It's the only thing that's going to be changing it for our differential area is going to be this DH right here. How do we know what that width is going to be? Well, just as before, we have this circle. We have basically a unit circle. And what we want to do is we want to get things in terms of theta, in terms of polar coordinates, you could say. So what we have is, like before, we have this, and our height was R sine theta, so what's our width going to be? Adjacent to our theta. It's going to be this right here. It's going to be adjacent over hypotenuse. So that's going to make our width equal to what? It's going to be R cosine theta, which means that this is going to be our differential area is going to be equal to the width multiplied by the differential height. Now what we can do is we can start to plug in some of these equations. But I thought that before that, I'll probably make a cut because this is going to be a lot of integrating and a lot of things like that. So we're probably going to have a completely blank board for that. Just leave our integral up here. But either way, we should determine what our bounds are going to be. I told you that we were going to be integrating from this point up here, the H value, the height of the fluid, all the way down to the bottom. So we can call this value theta 2. Now what's theta 2 going to be? That's going to be negative pi over 2. Think about an xy coordinate, a unit circle. That angle directly below is going to be negative pi over 2. So what's this theta 1 going to be? So let's look at what we have. How are we going to figure out that angle right there? Well, first we need to realize what we're going to do is we're going to be using inverse sine to figure out that actual theta. Because there's really no way of doing it, and it needs to be case dependent. So what we're going to have is we're going to have this sine, inverse sine, to give us that angle. Now, how do we determine what's going to be inside of that? Well, we actually do know what's going to be inside of there. Because what we're going to have is we're going to have our total height right here. What we're going to do is we're going to subtract our radius, and then we're going to divide by our hypotenuse. So simply what that's going to be is theta 1 is going to be equal to the inverse sine of, sorry, I already forgot, it's going to be equal to h minus r over r. So this is going to become important later. I'll probably write a lot of these terms down here, put the integral up here, get rid of our circle just to make a lot of room, because this is going to be a little bit intensive when it comes to math, reorganizing, plugging in values. So yeah, see you in a sec. So hello everyone, we are back. We have made some room for our integrations that we're going to be doing, and I have listed all the terms that we have previously created expressions for, derived, all these expressions on the side, including our theta 1 or theta 2, which are going to be our bounds of integration, and the rest I'll just explain as we go. All right, so let's just get right into it. So we know that our force from before, it's going to be the same thing. It's going to be the integration of our pressure and our differential area. And what we're going to do, I'll talk about later, is those bounds, which we have found before. But we'll insert those once we actually get into the substitutions and everything we're going to make. So what is our pressure? We know that it's rho gh from before. And then our differential area is going to be our width multiplied by our differential height. And okay, so what can we do with that? We just plug things in. And what I'm actually going to do is I'm going to remove these rho g terms right away. So what we're going to have is rho g on the outside. I don't know if I made that clear. And we're going to be integrating, and I'll add these theta terms in now, from theta 1 to theta 2. And I may have made a mistake with our bounds of integration, so that the arc sine of height minus the radius over our hypotenuse term, that might have had to been theta 2, and then our theta 1 should have been negative pi over 2, but it doesn't make a difference. We're just going to have some negatives that are going to be flipping around. In the end, it should be okay, but we might have a little bit more negative trouble. So we'll just go along with it. So what do we have left? We have the rho g gone, and then what we're going to have is we're going to have our h term, which we know is r plus r sine theta. And then we have our differential area term, which is going to be our width, which is r cosine theta, and then our differential height, which is also r cosine theta. So what we're going to do is we'll just combine those into r squared cosine squared theta d theta. So I'll go ahead and write that now. R squared cosine squared theta d theta. Now, in addition to our rho and our g term, the density of our fluid, and then the gravitational constant, we have another constant in r. And what we have is we have r squared right here, and then these two can be transformed into another r that we can pull out, so r cubed. So let's just write that. It's going to be equal to rho g r cubed integrated from theta 1 to theta 2. Excuse me. And then what we're going to have inside of there is that's going to become a 1. So cosine squared theta plus sine theta multiplied by cosine squared theta. So sine theta cosine squared theta d theta. That's a really nice integration. Not actually, I take that back. It's not a very nice integration. What we're going to have here is, I believe that it's integration by parts twice. And then what we're going to have over here is, I believe, a trigonomic substitution. But we're not here to do a bunch of calculus. So I believe what I'll do is I'll just make a quick cut, get a little bit more room, because this is going to become very intensive when we actually have to plug in our Theta values are bound values. I guess what I could also do is make these dummy integrals of dummy variables of integration. But what I'm going to do is I'm going to make a super quick cut. I'll probably just have what we need to be done. So it's going to be basically what we're going to have. We're going to have rho g r cubed, and then what we'll have is we'll have that multiplied by whatever these are, and we'll have this evaluated from theta 1 to theta 2, whatever these may be. I'm not 100% certain. I guess I could make a little guess. I think it's 1/3 cosine cubed theta. I believe that this is 1/2 theta plus sine theta cosine theta, but I just want to be sure, make sure that I get everything right before we actually start plugging in and getting our final term for the final expression for the force going along out normal to the surface of the end cap. So, thank you. All right, so hello everyone, we're back. What I've done is I've created some board space. I've left our first force that is acting upon the curved surface of the barrel. And what we have now is we have what we need to do to figure out the second force that is acting upon the end cap. So what we have is we have 1/2. For our first term, we have 1/2 theta plus sine theta cosine theta. That's going to be our cosine squared theta term that we had in our integral, and that's what we get when we integrate it, although we do have to plug in our values for our bounds. Either way, and then we are going to subtract 1/3 cosine cubed theta, which is going to be our sine theta cosine squared theta term. So let's just get right into it. So the first thing that we know is that we're going to have our force is going to be equal to, and what we had was we had the, I believe it was rho g r cubed, and also we're going to be multiplying this by 2 because we were only talking about the 1/2 of the cylinder, so we're going to be making up the whole part of the cylinder. Sorry about the scribbling. Throw that right there. And then what we're going to have is we're going to be evaluating. So the first thing that we need to see is that we have this negative pi over 2 term. And what does that mean? For that, that is simply going to mean that all of these, the cosine is going to be equal to 0, meaning that all we're going to be left with is 1/2 theta, because both of these are going to cancel out, become 0. So what we're going to be left with is, I'll just make a big multiplying bracket for us, because we're going to have a lot of terms. I believe we're going to have 4 terms that we're going to have to figure out. First couple are going to be the easiest, so we're going to have negative pi over 4, it's negative pi over 2 to that. And what we also need is we need to include this term as well, so we are going to subtract 1/2, and then arc sine for our other bound that we determined, arc sine of the height minus our radius over our hypotenuse radius. So that takes care of our first part of our integration. Now what are we going to do for the rest of it? So what we have is we have this this arc sine term that I was just talking about, and what we're going to do is we're going to insert that in for theta. Well, if you realize right here, what we're going to have is, and this just comes from this right here, by the way, if I didn't make that clear, this first bound, we're subtracting that because that's going to be our 1/2 theta term. Hopefully that makes sense. So now what we're going to be left with is 1/2 sine theta, and again, our theta is arc sine. So what we can do is those cancel out, and what we're going to be left with is simply just what is inside of our arc sine, which is the height minus the radius over the radius. So 1/2, this is going to be multiplied by, 1/2 sine theta, which is going to be, just h minus r over r. And then what are we going to do with this cosine theta term? How are we going to determine this? Well, like I said before, I mentioned briefly the unit circle. This is going to become useful again for us because we know a very good property of a unit circle. We know that sine squared theta plus cosine squared theta is going to be equal to 1. Do a little bit of reorganizing. So cosine squared theta is going to be equal to sine squared theta. And then we take the square root of this. So 1 minus sine squared theta is going to be equal to cosine of theta. Now, what do we know about this 1 minus sine squared theta term? Well, what we know is that we already know sine theta, so what we can do is simply just square that term. And what is sine theta? As I just told you, it is simply just the h minus r over r. So I'll actually do this over here to leave us some room. So we're going to have cosine theta. It's going to be equal to the square root of 1 minus h minus r squared over r squared. Now I left that over here, and there's still a 1 here, but real quick, r squared divided by r is 1. So we're just simply going to make this an r squared, if that makes any sense. Because we had 1 minus sine squared theta. We moved this r squared from the denominator of our original bound, what was inside of the r sine theta. Just to simplify things in the end, we're going to have a little bit of cancellations, and this will just make our lives easier in the end. So continuing, let's do a little bit of some manipulation right here. So let me go silent for a second. As I can explain, h minus r squared is equal to h minus r multiplied by h minus r. And then what we're going to get is h squared minus rh minus rh, so minus 2rh plus our r squared. So what's going to happen is this is going to cancel out with this up here. And let's start moving this over here. Or I guess I'll simplify first. So what we're going to be left with is h squared minus 2rh, just so I can erase this real quick. So cosine theta, can you see this? I believe you can. Cosine theta, I'll go on this side. Cosine theta is going to be equal to the square root of our h squared minus 2rh over r squared. In the square root, sorry, this should be like that. I didn't include the denominator in there. I meant to, just a little bit of mess up on my part. So what this is going to become is this going to become r in the denominator, because I guess what we could do, square root of a fraction is the square root of the numerator divided by the square root of the denominator, so that becomes an r. And yeah, we just plug that in right here, and we can simplify this term. So real quick, square root of h squared minus 2rh over r. So what does this become? I'm going to plug it in up here. Try and keep it clear and concise as we go, limiting terms that we don't need to hang around. So this is going to be 1/2. And this is also going to be a subtraction, I believe. Yes, this is going to be a subtraction, and this term will become positive in the end when we plug in the cosine, the minus 1/3 cosine cubed theta. Getting ahead of myself again, but plug this in. This is going to simplify to h minus r over r. So it's going to be h minus r multiplied by the radical, the square root of h squared minus 2rh. That is going to be over 2r squared. Yep, 2r squared. Okay. That looks pretty good so far. F2, let's make that equal. Oh, equal to the 2, like I said, both sides. I forgot to insert that. It's moving a little too quick. Okay. So now all that we have left is this minus 1/3. And then we know what our cosine theta is, which I can't believe I just erased. Well, that stinks. Believe that it's just this h squared minus 2rh over r. That is what it is, so I'm just going to plug that in. Should have left it up there to prove it, but that's what I derived earlier. I had the cosine theta, and then I did the reorganizing and everything. But what we can do is we can just simply plug that in. So we have negative 1/3 multiplied by h squared minus 2rh over r. All of this is going to be cubed because we have the cosine cubed right there. So when we plug it in, I'm actually just going to write it right here. So I'll make this kind of try and center it. So then that minus is going to become a plus because that is our lower bound. You subtract the lower bound from the upper bound. That's what we've been doing. So this becomes a positive. So we're going to have a positive 1/3. Oh, I'll write that a little better. Plus h squared minus 2rh to the 3 halves, because we had that square root. When you keep a square root, you still have to keep that there. Then that's going to be over 3r cubed. Now, would you look at that? After a bit of manipulation, doing some polar coordinates, unit circle, a lot of different manipulations, what we have found is we have found this equation. Though it may not be the most pretty thing in the world, this is what we're going to be rolling with today. And actually, I think that it's a pretty good equation. Because simply you just plug and chug, you get through it, and you figure out what that second force is going to be. And when you combine that with the first force equation, which we have over here, the 1/2 density of our fluid times the gravitational constant times the length of our barrel or cylinder multiplied by h squared. Then you include this as well. You put those two together. What we're going to have is we have figured out two expressions. We have figured out the expressions for the force that is exerted on a cylinder by the liquid inside. And I thank you all very much for watching, and I'll see you next time.